Welcome to the Deep Dive, where we take complex source material and pull out the surprising takeaways for you, fast. Today, we're looking literally beneath our feet at places where the Earth is splitting open, actively, sometimes dramatically.
Yeah, it's a fascinating topic because the sources show these two really different ways the planet breaks apart. You've got, on one hand, this huge, almost unimaginably slow geological separation, stuff that builds continents over millions of years. And then, completely different, you have these localized cracks, sometimes appearing almost instantly, and often linked to what we're doing on the surface.
Right, the contrast, the timescales, the causes, that's really our guide for this deep dive. We'll go from like a geological train wreck unfolding over ages in Africa and the Pacific Northwest to this, well, frankly, terrifying moment caught on CCTV in Myanmar where the ground split 2.5 meters, and also this spreading environmental crisis, these man-made fissures cracking open the American Southwest.
Exactly. It's a real study in extremes. So maybe let's start big. Planetary scale.
Let's do it. Okay, so our sources point us first to the biggest active continental split we know of, the East African Rift, the EER. This isn't just some crack. This is, well, the African plate actually dividing. It's heading towards becoming two separate land masses.
Yeah, it's basically the birth of a new tectonic boundary. You've got the main African plate, scientists often call it the Nubian plate now, and then the piece breaking off to the east, the Somali plate. They're slowly peeling apart.
I always think of plate tectonics as, earthquakes, sudden violence. But the sources stress how slow this main movement is. How slow are we talking?
We're talking millimeters, about 6 to 7 millimeters a year. Think maybe the thickness of a few corn stacked up. That's how much further apart they get each year.
Okay, tiny year on year.
Mm.
But the long-term result, that's the mind blower. Geologists are projecting, 5 to 10 million years from now, that whole Rift Valley sinks, the ocean floods in, and you've got a new sea splitting Africa.
That's the ultimate end game, yeah. But the stress doesn't always release slowly. Sometimes it goes fast. Remember that event in 2005 in Ethiopia, in the Afar region?
Oh, yeah. That was incredible.
Right. That's a triple junction, Nubian, Somali, and Arabian plates all pulling away. And boom, over just a few days, this massive crack opens up, nearly 35 miles long.
35 miles. And the sources said that one event was like hundreds of years of normal movement crammed into days.
Exactly. That's when you see the slow creep suddenly accelerate. It's like a preview of how continents are actually born or reborn.
And that Afar Triangle region, it's a living laboratory, they call it.
It really is. And you see the energy potential, too. Countries like Kenya, they're already tapping into that immense heat from the thinning crust for geothermal power.
Geothermal sounds great, clean energy and all that, but if you're drilling right into a zone that's actively tearing itself apart, what are the risks there? Is it stable?
It's definitely a calculated risk. The energy source is huge. Magma's closer to the surface. But that closeness means you're living right on top of the earthquake generator, the fissure maker. So yeah, they're managing pretty significant instability to get massive energy returns. It's a trade-off, harnessing planetary power versus managing its inherent dangers.
Okay, so that puts the slow 667 millimeters into a different light. Now let's shift gears a bit. From a continent splitting apart to the Pacific Northwest Cascadia, where it looks like a tectonic plate is dying.
Yeah, this is another really cool, rare thing scientists are witnessing. You've got these oceanic plates, the Juan de Fuca and the smaller Explorer plate, diving beneath North America. That's subduction, but it seems like they're tearing themselves up before they fully subduct. They're breaking apart on the way down.
And I liked how one source put it, it's not like a sudden stop, but more like death by 1,000 cuts.
That's a great analogy, isn't it? It's not one big failure. Scientists call it piecewise or episodic termination. It's like, imagine a huge train derailing, but super slowly. One car buckling off at a time instead of a head-on crash. The plate seems to be fracturing into these smaller bits, microplates, and this whole process just slows everything down until the subduction eventually stops in that section.
So it's not a smooth dive, it's getting shredded.
Yeah.
And that fragmentation is basically putting the brakes on.
Pretty much. And they can see this using seismic reflection imaging. It lets them map out deep fractures. There's one huge offset they found where a chunk of the descending plate has dropped like 5 kilometers compared to the bit next to it.
Wow.
And what's really neat is by seeing this happen now in Cascadia, we can look back at old geological puzzles like these weird fossil microplates they found off Baja California ages ago. Now we're like, okay, this is probably how those formed. We're seeing the mechanism in action.
Okay, so we've looked at these immense, unavoidable planetary forces, things playing out over millions of years. But kind of astonishingly, we're also creating our own ruptures right near the surface.
Yeah.
We're shifting from continents moving to, well, potentially our own driveways collapsing.
Yeah, that's the big pivot here, isn't it? We go from deep tectonic drama to something immediate, visible, and depressingly human-caused. We're talking about earth fissures and land subsidence, especially in the U.S. Southwest, Arizona, Utah, California. They're seeing a lot of this.
And the sources are really clear. These aren't natural fault lines acting up. These huge cracks are an anthropogenic hazard, human-caused. And the cause is directly linked to our thirst for water, right? Pumping out too much groundwater.
Exactly. We are literally deflating the land. Aquifers, underground water reservoirs, get drained faster than rain or rivers can refill them. The sediments, the sand, and clay that were held apart by water pressure, they compact, they settle. The whole basin floor sinks that subsidence. And that sinking creates massive tension, especially around the edges of the basin, which pulls the ground apart, forming these fissures.
And the scale you mentioned in Arizona is kind of hard to grasp.
Mm-hmm.
Fissures across 5 counties. An aggregate length of mapped cracks at 169 miles. Like, what does that even look like on the ground? Is it a giant chasm or?
It can be both. Sometimes they start small, maybe look like just a crack in the dirt, but they are deep structures. They can grow to be, maybe 2 miles long, easily 15, even 25 feet wide at the surface.
Yeah.
And they've measured them going down 90 feet. But geoscientists think they often connect much deeper, maybe right down to where the water table used to be. They're like these huge scars tearing across the landscape.
And the danger to buildings, roads, canals, infrastructure must be huge. The costs mentioned.
Oh, the costs are astronomical and getting worse. That one example cited, repairing a single irrigation canal near Scottsdale Air Park back in 2007, $820,000.
Just for one canal section.
Yeah. And when they were building the Loop 202 freeway near Phoenix, they had to spend $200,000 just to deal with one fissure they encountered during construction. We're literally spending fortunes because the ground itself is breaking apart due to water use.
And the really sobering part is the water scarcity underneath it all. Some experts were quoted saying that certain basins in Arizona are so overdrawn, the aquifers are so depleted, they're never going to bounce back.
That's the really scary part. It suggests this isn't temporary damage. The fissuring, the subsidence, it might be a permanent change to the landscape because the underground structure is fundamentally altered.
We've crossed some kind of threshold.
It seems like it. In some areas, yes, we've pushed the system beyond its ability to recover. And just quickly, while we're on cracks, it's probably good to point out these earth fissures are different from sinkholes. People sometimes confuse them.
Okay, yeah. How are they different?
So fissures, like in Arizona, are tension cracks. They form in loose sediments, sand, and gravel when the ground sinks due to water withdrawal. Sinkholes usually happen in what's called karst terrain places with limestone or similar rock that dissolves easily. Think Florida, parts of Texas. There, you get underground caves or cavities forming naturally. If the water table drops, or sometimes just due to weight on top, the roof of that cavity collapses inwards. That's a sinkhole. So both can be made worse by humans messing with groundwater, but the basic geology, the way they form, is totally different. Fissures are pulling apart. Sinkholes are collapsing inwards.
Got it. Pulling apart versus collapsing in. Makes sense. All right, so we've gone from millions of years of continent splitting to decades of human-caused ground failure. Now let's zoom into just 1.3 seconds, because this next bit involves a scientific breakthrough that was almost accidental, captured on a regular security camera.
Yeah, this is amazing. Scientists actually saw the Earth's surface rupture during a big earthquake. It happened in central Myanmar, March 2025, a powerful magnitude 7.7 quake on the Sauging Fault. And just by chance, a standard CCTV camera was pointed at the right spot at the right time and recorded the ground tearing apart during a strike slip rupture.
Strike slip meaning the ground moves sideways, right? Not up and down.
Exactly. And the video gave clear visual proof of something scientists had mostly just modeled before. What did that 1.3 seconds actually capture? It showed the ground shifting sideways, displacing by 2.5 meters. That's like 8 feet.
Wow.
In just 1.3 seconds. It was moving at about 3.2 meters per second during that slip. And having that clear visual, that kinematic data, the actual motion and speed, it confirmed a couple of really important ideas about how faults break.
Okay, what were those ideas, and why did seeing it matter so much?
Well, first, it backed up the theory of pulse-like rupture. The idea that the slip, the movement along the fault, isn't usually a slow grind over the whole length. It's more like a concentrated burst of movement, a pulse of energy that travels really fast along the fault line. Seeing that high velocity on the camera really helped confirm that model.
Okay, a pulse, not a slow tear. And the second thing?
The second thing challenged a common assumption. Many models sort of assumed faults rupture in a relatively straight line, just for simplicity. But the analysis of this video showed the path of the rupture was actually subtly curved.
Curved. Okay, why is that significant?
It means researchers need to build more complexity into their models. They can't just assume straight lines. The actual 3D geometry of the fault matters for predicting how the ground will shake.
So this isn't just cool science theory, right? This has real-world safety implications. How does seeing this help?
Oh, hugely. This kind of detailed kinematic data, seeing exactly how fast and in what pattern the ground moves during a rupture, it's a practical tool, as one source put it. It lets scientists fine-tune their earthquake models. It helps them improve early warning systems. If you understand the rupture dynamics better, you can potentially predict the shaking intensity more accurately, maybe giving people those crucial extra seconds, possibly even minutes, of warning in earthquake zones worldwide. This CCTV footage is literally helping make those systems smarter.
Amazing what you can learn from a security camera. #outro. So bringing this all together, what have we seen in this deep dive? We've really looked at two very different kinds of Earth splitting. You've got the planet's own massive slow-motion tectonic engine, like the East African rift grinding towards creating a new ocean over geological time. Deep, powerful, inevitable.
And then, completely contrasted, you have the immediate, very localized, and often very costly results of our own actions. Specifically, pumping groundwater to the point that the land itself starts to tear apart in places like the American Southwest.
It seems the unifying factor here, whether it's deep magma or surface water pumps, is tension, right? The force required to pull the crust apart.
Absolutely. All these examples from the era to Arizona highlight just how the Earth's crust responds when it's put under tensional stress.
And everything we learned, whether it's watching a plate die slowly off Cascadia or capturing that split-second rupture in Myanmar, feeds back into understanding and hopefully mitigating the hazards.
Definitely. Which leads us maybe to a final thought, circling back to the East African rift. That ongoing split, it promises huge geothermal energy, yeah. It will eventually give landlocked nations new coastlines, completely redrawing maps and economies, but it also guarantees instability, earthquakes, eruptions. So the big question we want to leave you with is this. As this process continues, maybe even accelerates, how will humanity manage the immense geopolitical shifts, the environmental changes, the potential chaos that comes with the birth of a new ocean basin right through a populated continent?
That's not just geology anymore, is it? That's history in the making, unfolding under our feet. Something to think about.